we're basically going to see here is an introduction to three different representations of complexity, with a specific focus on the idea of complex systems. And in our vernacular, complex systems really mean that we're looking at systems where there's a process that's performed over certain inputs and delivers some kind of outcome. What we're going to use visual models in order to try and make this whole thing a little more, let's see if we can make complexity a little simple or a little simpler to understand. So that's the goal of what we're going to look at here. The kind of my visual models of these three are taking Holland's book on complexity, and which I'm considering more of a John Holland of a science and math view. Then I'm taking Margaret Hamilton's complexity, and I'm looking at the software engineering view that Margaret, the way she approached complexity, she and Sadine Zeldin, and then industry complexity from a Harvard Business Review problem solution matrix that was developed. And so it's that view of complexity from an industry perspective. So those are the three models that I want to look at. And so I think what we'll do is we'll start with Holland's. All right, now the model that I'm talking about here with regards to John Holland is from his book called A Very Short Introduction to Complexity. He has a lot more, and I haven't, and this is certainly not John's view of John's model. This is my view of John's model of complexity. But he talks about focusing on what are the mechanisms that because one of the goals here is to try and come up with some way that we can help manage complex systems. And we can only do that if we can understand how, what are the triggers, what are the leverage points in terms of a complex system, and where can we find them? And what we find in looking at least I found in looking at the book on complexity by John, is that as he searches for these mechanisms, what we tend to find is that no matter how complex the process may appear to be in the middle, it's not really where we're going to determine that complexity occurred. Right now, the only thing we actually can work on is the inputs and the outcomes. And so if the inputs are adaptive, which means that the inputs are more like a moving target, if you will, then the mechanism in the middle, the process itself, has to be able to facilitate adaptation, which by definition makes it a complex process because it's facilitating adaptation. Also, if the outcome demonstrates emergence, and so the process in the middle is able to deliver emergence, then that is a sign of a complex problem. And if you think of that, emergence means that a property coming out at the outcome is different than any of the properties on the input. I think a good example that John gives is you have hydrogen and oxygen as your input. You put them together and it delivers water, and water has wetness. But the property of wetness is not true of either hydrogen or oxygen themselves. It's an emerging property of the combination of hydrogen and oxygen, which means that the actual combination process that's delivering emergence is really a complex process because it's delivering something that's different and it can't be summed from the properties of the inputs. Another example that John talks about in terms of looking at outcomes is unpredictable. So if the process delivers unpredictability, and he talks about Markov chains, and he goes through a lot of things about the predictability and unpredictability of the outcome. But if you note that the outcome is basically unpredictable, so it's something that we have kind of we can come up with some kind of idea of what it's going to be, or we can come up with some kind of probability regarding what the outcome is, but not specifically what it is, then we know that the process itself is a complex process. So those are kind of the three criteria that we get from that I got from reading John's book on complexity. But he still says that he thinks that we are moving in the future to where we will be able to come up with a way of looking at the process in the middle and coming up with some kind of way of patterning that and identifying that is complex. Now, so the idea then is that can we come up with what those mechanisms are? And we'll talk about the other two now so we can see how they relate. As far as Margaret Hamilton is concerned, when Neil Armstrong stepped on the moon, there were a number of red lights that popped up in that lunar landing module, and then NASA, looked at Margaret, and Margaret and Sadine Zeldin were the two of the primary project managers for all the software that was on the lunar landing module. And they looked down and they say, with all the testing that we did and everything that we did, how could it possibly, still show red lights once he got up there and landed? And Margaret took that on as kind of a challenge, if you will, to say, okay, so she tried to look at software engineering techniques. How can I, from a software engineering perspective, how can I deal with complexity? And James Martin wrote a book about Margaret's and Sadine's work. He calls it System Design from Provable Correct Constructs. And what basically it is it's a design technique where you get provably correct constructs that you use in order to establish a provable design. And that's how Margaret went after the software engineering process of going after complexity. So again, the focus though in this was also on the inputs and the outcome, right? And when you're looking at the inputs and the outcomes, one of the difference is that the process again in the middle is very hierarchical. In John Holland's book on complexity, he also talks about that fact that the processes are very hierarchical. But it's a hierarchical process working off of inputs. But the neat thing that Margaret came up with is that there's really only 7 basic relationships that occur in the relationships between all of the children in this hierarchy. And these are the 7, and I'm not going to go into detail about those 7. You can get that from James Martin's book. But the idea there is that there is a pattern to the way they're related. And this is the first time that when I was working with Margaret and with the tool, this was the first time that there was ever some kind of relationship drawn between the children. I mean, up to this point, most hierarchical structural tools are, a parent has 2 children and they do explode down that way, but they don't talk about the interrelationship. So I think that one of the golden nuggets that was uncovered here is that there are these 7. And it's very similar to the fact that like multiply is really, a whole bunch of adds. So you constantly have this buildup, which we'll talk about in a minute. So one of the other things is that Margaret talked about that, that in order for the software engineering, in order to be able to validate this whole thing, you have to be able to type the input. You have to be able to say that this input is an integer. This input is even an adaptive agent, all right? But you have to be able to type that input and type the output. And so when you have those inputs and outputs typed, the only way that works is that if you can layer these things over some kind of primitive. So the best example again would be say the add primitive. And the add primitive says that I have an outcome and there's only one of them, and it's an integer, and the input can be 2 or more integers. And therefore, if you were when I was working with this tool, if you actually brought in a real number into this particular process, the system would kick it out and tell you that basically you're bringing in a non-integer, and therefore I can't guarantee that this thing will work. So what it did is kind of it was a gatekeeper against inputs that didn't fit the type that it needed that it knew it needed in order to produce the outcomes. And that's how the whole product was. They built a product for this called 001, but that's how the whole product was structured. It was structured around this concept of typing inputs and outputs. One of the issues here, again, we talked about the integers and that they both have to be integers, and this is an add integer. You could have an add that is an add with real, and you could have real as the type of the inputs and type of the outcome. But for our example here, I just use the idea of integer. One of the other neat things or golden nugget I'll call it from the software engineering uh, one that Margaret presented is this idea of absorption. And absorption basically says that the outcome absorbs the input. Now it's not always true, and only certain inputs get tagged as being absorbed in the process because some could just have the state change. But but the interesting thing is that it's and if we take a good example of someone buying a car, right, and they have a cost is one of the inputs, and the interest that they have to pay on the car if they're going to get a loan, and then so the cost and the interest together get added together, and the outcome is the loan amount. Well, from that point forward in your hierarchical structure, the loan amount is all that you can talk about because the loan amount absorbed the cost and the interest expense. So you can't independently now start doing things with the cost and dividing that by the number of months to come up with some kind of average for what the payment is because it's the loan amount that is now it already absorbed those. And that's a simple example, but it really has a very powerful absorption is a very powerful concept in the whole way of making sure that you can deal with these with a complex system and with the way that the system interfaces and making sure that you're not using something multiple times. The idea of emergence sits inside of the software engineering process here. By the outcome could have it could actually be an outcome that has an emerging property to it. But the idea is that emerging property would also have to work its way either towards all of the siblings of this process or up to the parent and up from that parent and to its parent. So and John talks about that. John Holland talks about that too. Is that in the hierarchy that emergence has to also show its way up the process in the hierarchy. It can't just you can't just have something that just emerged and then disappears, if you will, in terms of the process. And that's one of the things that's really neat about the tool that I was using with Margaret. Now, as far as unpredictability goes, there's still a question as far as how software engineering would deal with unpredictability. I mean, you can build the software engineering for Markov changes, and it can produce probable outcomes and stuff like that. But you're still going to have a complex process that you don't have a set pattern for. And probably, I can't think of a way that you could actually break that down into something that will be a predictable. Be, be, so you still introduce this idea of unpredictability into the whole software engineering, so that you would know that you're getting an output that's unpredictable, and you would know where that unpredictability exists in the whole process, and you would know that your unpredictability, it's neat because in software engineering, the unpredictability would multiply itself out across these processes, so that if you had 6 children and they all were unpredictable, then the parent would be the multiple of all of those unpredictabilities, which would be so the parent would be even more unpredictable, if you will, than all, because it's the sum of the unpredictability of the children. But that's kind of where Margaret went with that. Now let's go to the Harvard Business Review article, because that was a little bit different. It really approaches the problem in a whole different way. The Harvard Business Review article approaches the problem from the point of view, it focuses on problem type. So it says that it basically identifies 4 different problem types, which I think is really neat. I think that's something that we should consider adding to John Holland's model and possibly to Margaret's model. But it talks about common, complicated, complex, and chaotic. So it breaks in the John Holland book, there's a lot of discussion about the difference between complicated and complex, but it also assumes chaotic is part of complex. And this actually model works differently. It says that there is a difference between complex. So there's 4 rather than 3 different ways of looking at this. And then it says that based upon that, there's a relationship between what the solution type is and what the problem type is going to be. And then we can build patterns for the solution types. Now let's go through an example, okay? If it's a common problem, and even if it's a messed up Rubik's cube, there really is only one right best practice solution where it all gets together and it's all so that there is a solution to common problems, and it's one right best practice. complicated problems in the industry model says that there's one right best practice solution, but it's within context. If I take it out of industry and put it into politics, let's say that democracy, that now we have 150 nations, and almost every single one of them recognizes democracy as the best practice. But yet, democracy as it's practiced in the United States is different than democracy as it's practiced in Europe, or as it's practiced in Japan, or as it's practiced in other countries. So even though there is one right best practice, the solution itself is different within context. So that there are complicated issues involved in looking at it that way. The other issue is that when you look at complex, is that there is a best practice pattern solution for complex for these types of problems, but that best practice solution is a methodology. There's no cookbook approach. There's no a fixed solution. It's not a recipe for how you solve the problems. Instead, it's a methodology, and works its way through. The methodology we're looking at here is, say, a methodology for a software solution, which says that it has a pattern, and there is a patterned way of going after that problem. And I think that's one of the things that Holland was talking about, is that we're looking for some patterned ways. And what we're saying here is that there are complex problems, but there is a pattern, and the pattern may be different for the different types of problems. The scientific complex problem or a biological complex problem would have a different methodology, but there is a set pattern to the methodology that may represent the best practice for that. And that's one of the things that I think that John indicates that he's looking for. Now, however, when you get over here to the chaotic is really where it's looking at what works solution. And I think that a lot of what John talks about fits more, at least from this model perspective, into the chaotic world, where it's looking for what works. We don't really have, so we're looking at the output and the outcome to see what occurred, and constantly searching that output as to see what occurred, to see if we can come up with a solution. So basically, let's look at the complicated down here, or tend to be where there's multi-dependencies. All right, we think we'll find that is very common for complicated problems. So that they, linear, multi-dependency solutions. Whereas if you look at complex versus chaotic, you're really looking at multi-dimensional. What the way the industry breaks it up is that the complicated problems versus a complex problem. A complex problem is a multidimensional problem. We tend to treat so many problems as if they're only two-dimensional, and really they are three-dimensional. And I actually think that we're going to see a whole lot of problems in the future moving from the complicated to the complex world, only because we start to really recognize that problems really have more dimensions than we're giving them. And because we have right and a left hand, we tend to try and get problems down into two dimensions, making them two opposable dimensions, and it makes it easier for us to work it that way. But this is more complex. Is more like we have to use linear algebra type tools in order to come up with multi-dimensional solutions, and we have to use the same process and the same techniques and patterns that you would use for for linear programming solutions. So that's an even extending linear programs on top of multiple dimensions, time and other dimensions. So again, the complex world tends to be multidimensional. The chaotic world is, again, where we pick up the unpredictability, right? That's where being unpredictable, means that we actually have to come up with some kind of way that we're going to determine what works. In other words, what do we define as what works? So we have to come up with some kind of, I have them here in the industry, they use scorecards, which is, they have benchmarking criteria that they want to use to determine what works. So, let's go, because when we zero in on something that here's what we expected, or here's what we were looking for, and we're looking at the outcome, we find the outcome that we're looking for, then we look at the processes that got us there and say, okay, then can we replicate that process, or is it worth replicating? Because are the inputs or the factors coming into the process going to be similar? And if they are, then we can possibly replicate it. And so we use metrics. We have stage gates concept, which says that basically it's a moving target. That's why you kind of see it as a spiral here. It's a moving target where we're constantly assessing where it went. This is very important from an industry perspective because for industry, what it tells them is that when we were using this with companies, it was telling them that when the problem actually falls into the chaotic realm, then we're not going to build some kind of a fixed solution to go after it. Instead, we're going to build a whole bunch of small pieces that we're going to look at, and we're going to run it through these stage gates to constantly assess it to see if it's delivering what we want. And so we're constantly focused on the delivery, and it's almost like the chaotic is the world where you can't put to rest. The complex world, maybe we'll come up with the right methodology. It's multidimensional, has a lot of challenges, but if we come up with a methodology and we can get a team of people working on the methodology for those complex problems, then we can kind of put that to bed, if you will. The others, the common and complicated, we really feel like we can put those to bed. The chaotic problems, they're the ones that we are constantly focused on. Interesting thing in industry is came out of the article is that one of the issues revolving around industry best practices is that almost 80% or more of the differentiation that a business brings to the world is or to the rest of industry is in the chaotic section. That's really where their differentiation lies. And the way that they deal with the chaotic and the way that they handle those is what makes them different and better than another alternative choice. And that's how they can distinguish themselves and differentiate themselves. So differentiation exists up there in the chaotic. So it's interesting that it exists in a world where there is no real best practice. So that's kind of how industry kind of went after that problem. So basically what we're saying here is that can we take Holland's complexity, the science and math view, the software engineering view from Hamilton, the industry complexity, the view from the Harvard Business Review, and can we kind of merge them together to come up with some patterns and some pattern recognition for options and techniques that we use for complexity. And that's kind of